Before time began, something already existed. We have been taught that the Big Bang created everything: space, matter, even the clock that measures it. But the oldest light in the universe carries scars that should not be there. Patterns written before our cosmos was born. Echoes of something that lived and died so that we could begin. Scientists who have studied these signals do not sleep easily. We will follow them into the mathematics that breaks, the ghosts in our ancient light, the universe that bounced back from death, and the mirrors of time that run in directions we cannot follow. If you find this journey unsettling, share it and subscribe, because others need to hear this. Prepare yourselves. We begin. Picture the moment everything you know was born. Every atom in your body, every photon that warmed your face this morning, every galaxy visible from any telescope humanity has ever built. All of it erupted from a single point smaller than the period at the end of this sentence. That moment is what we call the Big Bang, and for most of recorded history, both science and philosophy agreed on one point with unusual unanimity. Asking what came before, it was a meaningless question. Physics itself was supposed to begin there. Space and time were created at the Big Bang, including the matter and energy within them, and the very framework in which anything could exist. Before was not a word that applied to anything real. It was a grammatical construction without a referent. This was the official position of cosmology for decades, and it held for a good reason. The mathematics of general relativity, our most powerful and precisely tested description of gravity and space-time, quite literally breaks down at the origin point. Run the equations of general relativity backward through the expansion of the universe, tracing matter and energy back through ever-increasing densities and temperatures, and everything converges toward a singularity. Every physical quantity, density, temperature, space-time curvature, shoots toward infinity as you approach the moment of origin. Infinity, in a physics equation, is not a real answer. It is a mathematical signal that the theory itself has failed, that it is operating outside its domain of validity. The equations of general relativity, even while describing the universe with extraordinary precision in every other context, cannot describe the moment of the Big Bang or anything before it. But over the last 3 decades, a different kind of question has been growing within cosmology. Quiet at first, and now impossible to ignore. It is not the philosophical question of what filled the void before time began. It is an observational and mathematical question. Are the specific physical conditions we observe in our universe today fully and adequately explained by a simple beginning at the Big Bang? Or do those conditions require something to have existed and shaped things before that moment? The question has become harder to dismiss as the data has improved, and the answer, arriving from multiple independent directions at once, is making physicists deeply uncomfortable. Observers analyzing the ancient light of the CMB have found patterns that the standard model cannot explain. Theorists developing quantum approaches to gravity have discovered that the Big Bang singularity is not real, but is replaced by a transition from a previous cosmic state. Physicists building on string theory have proposed that our Big Bang was a collision between membrane universes in a higher dimensional space, a collision that has been happening cyclically for an eternity. Each of these avenues leads to the same conclusion, expressed in different mathematical languages. Something was here before our universe began. The story that follows traces each of these avenues to its source. It introduces the physicists who built these frameworks and what they have staked their careers on. It follows the evidence through the oldest light in the cosmos, through the equations of quantum gravity, through the topology of extra dimensions, and through the disturbing implications of a cosmos without a beginning. At the end of that trail, there is no comfortable resolution. There is only a universe that, in the best current understanding of physics and cosmology, has been running in some form forever, with no first moment, no original cause, and no mechanism to explain why existence favors existing over not existing. That is the destination, and it is stranger than anything the standard story of the Big Bang prepared us for. The convergence is what makes this moment extraordinary. Scientists working in completely different theoretical traditions, using different mathematical tools, and starting from different physical observations, are all arriving at the same conclusion independently. Loop quantum cosmologists find that their equations demand a universe before the Big Bang. String theorists find that their framework generates an eternally inflating background from which bubble universes nucleate. Cyclic cosmologists find that the same mechanisms that produce our universe naturally produce predecessors and successors. The evidence is not coming from one place. It is coming from everywhere at once. In astronomy, distance and time are the same thing. When you look at a star 1,000 light years away, the light reaching your eye left that star 1,000 years ago. You are not seeing where it is now. You are seeing where it was, 1,000 years back in the past. The further away an object is, the further back in time you are observing it. Take this principle to its extreme. Look as far back in time as any telescope can reach, and you arrive at the most important relic in all of observational science, the cosmic microwave background. The CMB is the oldest light in the universe. It was emitted approximately 380,000 years after the Big Bang, at the moment when the cosmos had cooled enough for the dense, opaque plasma that filled it to thin into neutral gas. Before that moment, the universe was an impenetrable fog. Photons collided constantly with charged particles and could not travel freely. After it, the fog lifted almost simultaneously across the entire observable universe, and light began to stream in every direction. That light has been traveling through expanding space ever since. Its wavelength stretched from visible and infrared to microwave frequencies, its temperature dropping from thousands of degrees to just barely above absolute zero. The CMB was discovered by accident in the 1960s, when two radio engineers in New Jersey detected an inexplicable noise in their antenna that turned out to be the afterglow of the Big Bang itself. The discovery earned a Nobel Prize and cemented the Big Bang model as the dominant framework of cosmology. 3 generations of space-based observatories, each more sensitive than the last, have since mapped the CMB with astonishing precision. What they found was almost exactly what the standard model predicted: a nearly uniform temperature across the entire sky, with fluctuations of only about 1 part in 100,000, a nearly perfect map of the seeds from which all cosmic structure grew. But there are features in that ancient light that the standard model does not predict. The uniformity is not perfect in the ways the model expects. There are anomalies, real features of the data confirmed by multiple independent instruments and teams that sit unexplained in the CMB map like questions in a document that nobody has yet answered. Some of those anomalies are subtle. Some of them are startling. All of them are pointing in the same direction, towards something that shaped the universe before the Big Bang could have had any say in the matter. Learning to read those features is one of the central projects of cosmology today, and it begins with understanding the barrier that separates us from seeing them directly. The CMB is remarkable, both for its age and for its precision as a cosmological probe. The temperature fluctuations of 1 part in 100,000 encode an enormous amount of information about the physical state of the universe at the moment of emission, and about the specific statistical properties of whatever process generated them. Cosmologists can use the CMB to measure the density of ordinary matter, the density of dark matter, the rate of expansion, the geometry of space-time on large scales, and the specific spectrum of primordial fluctuations that inflated from quantum scales to cosmic scales in the first fraction of a second after the Big Bang. All of these quantities agree with the standard model to extraordinary precision. All of them except the anomalies, which point somewhere else entirely. There is a wall in time. It sits at the first 10 to the negative 43 seconds of cosmic history, a moment so early that no number you have ever encountered adequately communicates its proximity to the origin. If the entire current age of the universe, all 13.8 billion years of it, were represented by a single year, The Planck epoch would last less than a billionth of a trillionth of a trillionth of a second within that year. And at this wall, every physical theory we possess, every equation built over 3 centuries of scientific progress, breaks down completely. The Planck epoch is the moment when quantum mechanics and general relativity both apply with equal force, and both fail. In ordinary physics, this is not a problem because the 2 theories operate in entirely separate domains. Quantum mechanics governs the subatomic world with extraordinary precision. General relativity governs the structure of space-time on large scales with equal precision. For the vast majority of physical situations, including every situation ever studied in a laboratory, these 2 frameworks can be used independently, and neither contradicts the other in practice. But at the Planck scale, the energy densities and the space-time curvatures are so extreme that quantum effects and gravitational effects are simultaneously dominant. Quantum mechanics requires a stable background of space-time in which to define particle states and probabilities. General relativity describes space-time as a dynamic, curved geometry that responds to matter and energy. At the Planck scale, the geometry is so wildly dynamic that quantum mechanics cannot function on it, and the energy densities are so high that quantum fluctuations destabilize the geometry that general relativity tries to describe. Both theories produce infinities. Neither gives sensible answers. The result is a wall of fundamental ignorance that no telescope can penetrate. The cosmic microwave background, the oldest light we can observe, was emitted 380,000 years after the Big Bang, long after the Planck era had passed and the universe had settled into a regime where physics works normally. Everything between the Big Bang and the CMB must be inferred from the patterns in that light and from theoretical models. Everything before the Big Bang itself requires a theory of quantum gravity that does not yet exist in confirmed, experimentally tested form. What makes the situation genuinely strange is the depth of the ignorance. It is the specific features of the CMB that suggest the ignorance is hiding something. The Planck wall does more than separate us from an unknown past. It may be screening a predecessor from us, a cosmos whose fingerprints are nonetheless visible in the oldest light on our side of the barrier. The specific energy scale at which the Planck wall sits is not arbitrary. It is determined by the 3 fundamental constants of nature that govern both gravity and quantum mechanics: Newton's gravitational constant, Planck's quantum constant, and the speed of light. The Planck scale is the unique energy, length, and time at which all 3 constants combine in a way that does not privilege any of them over the others. Below the Planck scale, quantum effects dominate. Above the Planck scale, classical gravitational effects dominate. At the Planck scale, neither description is adequate alone. This is the regime where the true nature of space-time, whatever that nature is, must be described by a unified theory that combines both. In the direction of the constellation Eridanus, visible from the southern hemisphere on clear dark nights, there is a patch of the cosmic microwave background that is cold. Not cold in a way that sounds dramatic, because the temperature difference is expressed in millionths of a degree, but in the statistics of the CMB, where the entire dynamic range of the temperature map spans only a few hundred millionths of a degree, a region that is roughly 70 millionths of a degree below average, with a particular size and a particular surrounding structure, is statistically remarkable in a way that is difficult to dismiss. The cold spot was first identified in 2004 using data from the Wilkinson Microwave Anisotropy Probe and confirmed by the Planck satellite a decade later. Its statistical significance, the question of how often a standard cosmological model would produce something like it by chance, sits at roughly 3 sigma, meaning it would arise by random chance in fewer than 1 out of roughly 300 realizations of a standard universe. That is not overwhelming by the standards of particle physics, where 5 sigma is the threshold for claiming a discovery. But in CMB anomalies, 3 sigma is significant enough to require explanation. What makes the cold spot more troubling than its temperature alone is its geometry. The region is not simply colder than average at its center, with a smooth transition to normal temperatures. It is cold at the center and surrounded by a ring of slightly elevated temperature, a hot halo that encircles the cold interior. This specific profile, cold inside and warm outside, does not emerge naturally from any standard cosmological process. The most commonly proposed explanation invokes a supervoid, an enormous underdense region of the universe that the CMB photons pass through on their way to our detectors, losing energy through the integrated Sachs-Wolf effect. A supervoid roughly 1 billion light-years across has been detected in galaxy surveys in the correct direction, but the supervoid can only account for a fraction of the observed cold. The hot ring is not explained. The statistical anomaly does not fully resolve even with the supervoid included. The cold spot remains an open question, a feature of the oldest light in the universe that multiple independent analyses have been unable to fully explain using standard cosmological physics. And among the explanations still taken seriously by careful researchers is the possibility that it is not a feature of our universe at all. It might be a scar from before our universe existed. The power suppression at the largest angular scales in the CMB is perhaps the most quantitatively significant of all the anomalies. Standard inflationary models predict that the power spectrum of temperature fluctuations should follow a specific, nearly scale invariant form at all angular scales, with small corrections that depend on the detailed shape of the inflationary potential energy function. But the data shows that the power at the lowest multipoles, the patterns that span billions of light-years across the sky, is measurably lower than even the lowest inflationary predictions. This suppression is not dramatic enough to require new physics on its own, but in combination with the cold spot and the axis of evil, it forms a pattern that is suggestive of a physical process that operated before inflation, one that preferentially affected the largest scales in the universe. The cold spot does not stand alone in the CMB data. It has company, and that company was given a name that reflected the genuine alarm of the scientists who found it. In the early years of this century, cosmologists mapping the cosmic microwave background noticed that the very largest temperature structures in the CMB, patterns that span billions of light-years across the entire observable universe, were not randomly oriented. In standard cosmological models, these largest patterns should point in random, uncorrelated directions across the sky, as expected from a universe born from an isotropic and featureless initial state. What the data showed instead was alignment. Two of the largest multipole components of the CMB map, the quadrupole and the octopole, were correlated with each other in a way that statistical analysis said should happen by chance, less than about 1 time in 100. And they were both aligned in a direction that had no natural cosmological explanation, a direction suspiciously related to the plane of our own solar system and to the direction of our galaxy's motion through the cosmos. 2 cosmologists at Imperial College London coined the name the axis of evil for this anomaly, and the name was not meant as hyperbole. An axis in the CMB is cosmologically forbidden by the same foundational assumption that underlies the entire structure of modern cosmology, the cosmological principle. This principle states that the universe is isotropic, meaning it looks the same in every direction on large scales, with no embedded preferred axis, no directional structure, and no memory of any geometry that might have predated its formation. The axis of evil says the universe has a preferred direction. It was confirmed by the Wilkinson probe and reconfirmed by the Planck satellite a decade later using completely independent instrument technology. Every systematic error that could produce a false alignment has been carefully examined. None is sufficient to explain the observed alignment. The anomaly persists, unexplained. Among the possibilities that remain scientifically alive is the hypothesis that the axis of evil is a relic of pre-Big Bang physics, some feature of the state that preceded our universe, some directionality in the bounce or the brain collision or whatever transition produced the Big Bang, may have been incompletely erased by inflation, leaving a trace orientation, embedded in the largest scales of the CMB. If that interpretation is right, the axis of evil is a compass needle. It is pointing backward in time, toward a cosmos we can otherwise not see. The cold spot sits in a region of sky that has been the subject of increasingly sophisticated surveys. Follow-up observations using optical and infrared telescopes have mapped the distribution of galaxies in the direction of Eridanus out to various distances, and they have confirmed the existence of the supervoid, one of the largest underdense regions of the universe identified to date. The supervoid is real. The question is whether it is sufficient. Multiple independent analyses using different statistical methods have all concluded that the supervoid, while it contributes to the cold spot, cannot account for its full amplitude and structure. Something additional is needed, and that additional something remains unidentified. Among the proposals still being seriously considered is the possibility that the cold spot is a fossil signal from the universe that preceded ours. Before any theory of what preceded the Big Bang can be built, you have to understand precisely why the theory that describes everything since the Big Bang cannot describe the moment itself. General relativity is one of the most precisely tested theories in the history of science. The advance of Mercury's perihelion, predicted by the theory and confirmed in the early 20th century, the bending of starlight around the disk of our star, observed during a solar eclipse in 1919, the orbital decay of binary pulsars losing energy to gravitational radiation, confirmed over decades of observation by Joseph Taylor and Russell Hulse, earning them a Nobel Prize. The direct detection of gravitational waves from two merging black holes by the LIGO detector in 2015, confirming the last major untested prediction of the theory. Each of these confirmations has extended the range of conditions over which general relativity has been tested and found accurate. The theory works over an enormous range of scales and energies, but it contains a flaw that has been known since the theory was first written down, a flaw that Einstein himself was uncomfortable with. Under conditions of extreme mass and density, the equations break down. The curvature of space-time becomes infinite. The density becomes infinite. Time itself reaches an endpoint. This is the singularity, and it appears in two places in the universe. It appears at the centers of black holes, where gravity crushes matter past any conceivable density, and it appears at the Big Bang, when you trace the expansion of the universe backward to its origin point. In both cases, general relativity raises its hands and produces infinity, which in the language of physics means, I cannot describe what happens here. My equations are wrong in this regime. Something else governs this situation, and I am not that something else. The something else is quantum gravity, a theoretical framework that would describe space-time and matter at scales and densities, where both quantum effects and gravitational effects are simultaneously important. Building a confirmed theory of quantum gravity is the most significant unsolved problem in fundamental physics. Several approaches exist. Each of them agrees on one thing. The Big Bang singularity is not real. It is an artifact of applying the wrong theory. The road continues on the other side of that singularity, and what it leads to is the question driving everything that follows. The axis of evil sits at the intersection of two different unsolved problems in cosmology. One is the anomaly itself, the alignment of the largest CMB multipoles. The other is the cosmological principle, the foundational assumption that the universe is statistically the same in all directions. If the axis of evil is real and represents a physical feature of the universe rather than a statistical fluke, then the cosmological principle is violated at the largest observable scales. A violated cosmological principle means that the entire framework of modern cosmological calculations, which assume isotropy as a starting point, may need to be rebuilt from a different foundation. This is why cosmologists find the anomaly so disturbing. It challenges every calculation built on that assumption, and it challenges the assumption itself. In the year 2006, Abhay Ashtekar was sitting in his office at Pennsylvania State University watching a computer simulation. Ashtekar had spent decades developing loop quantum cosmology, an application of loop quantum gravity to the problem of the origin and evolution of the universe. Loop quantum gravity treats space-time not as a smooth, continuous fabric, but as a discrete structure, woven from quantum units of area and volume that cannot be subdivided below a fundamental minimum scale, in the same way that matter is composed of atoms that cannot be divided below a certain scale without reaching a different level of physical description. In loop quantum cosmology, this discreteness has a dramatic consequence. When the universe contracts toward extreme density, it eventually reaches conditions where the quantum granularity of spacetime becomes physically relevant. At those conditions, something happens that does not happen in classical general relativity. A repulsive force emerges from the quantum geometry itself. The more the universe tries to contract past the minimum quantum spacetime scale, the stronger the repulsion becomes. And at the Planck density, the repulsion wins. The universe does not compress to a singularity, it bounces. Ashtekar was so startled by the simulation showing this bounce that he asked his team to delay publication for 6 months while they checked every calculation for errors. When they published, the result was clear. In loop quantum cosmology, the Big Bang singularity is replaced by a quantum bounce. Time and physics continue through the bounce without interruption. On one side is a contracting universe. On the other side is our expanding universe. They are connected by the bounce, without any discontinuity and without any moment where the laws of physics fail. The prior universe in this picture was not a philosophical construct. It was a physical cosmos, governed by the same fundamental laws as ours, that underwent its own long history before contracting to the conditions that triggered the bounce. The Big Bang was not creation ex nihilo. It was a rebound, and the state of the previous universe at the moment of the bounce is directly connected to the initial conditions of ours, written into the quantum state of the universe that emerged from the bounce and eventually grew into everything we can see. The singularity problem in general relativity appears at the Big Bang, but it does not stop there. Every black hole in the universe contains a singularity at its center, a point where space-time curvature becomes infinite, and the equations of general relativity cease to apply. Physicists have learned to live with this limitation in the case of black holes because general relativity works so well everywhere outside the singularity. But the Big Bang singularity cannot be ignored. It is not the interior of a distant black hole. It is the origin of everything. Every physical question about the universe, every attempt to trace causation backward to its ultimate source, terminates at the Big Bang singularity and can go no further. The singularity is not a fact about the universe. It is a fact about the limits of the theory we are using to describe it. The implications of a pre-Big Bang universe in loop quantum cosmology extend beyond the mere existence of a previous cosmic state. They reach into the specific physical properties of the universe we inhabit today and make testable predictions about what those properties should look like if the bounce is real. In loop quantum cosmology, the quantum state of the universe propagates through the bounce. The fluctuations present in the contracting universe, their amplitudes, their statistical correlations, their distribution across different physical length scales, all of these are transformed by the quantum dynamics of the bounce, but they are not erased. They emerge on the other side of the bounce in a modified form, imprinted onto the initial quantum state of the expanding universe that follows. And those imprints eventually become visible in the cosmic microwave background. The most important prediction concerns the power spectrum of CMB temperature fluctuations at the very largest angular scales. In standard inflationary models, the power spectrum should follow a nearly scale-invariant form across all angular scales, with at most small modifications. But in loop quantum cosmology, the quantum bounce suppresses the power at the very largest scales, the scales corresponding to the lowest multipoles, the same scales where the CMB data shows the axis of evil alignment and the suppression that standard inflation struggles to explain. This prediction was made before the Planck satellite measured the power spectrum in detail. When the Planck results were published, the large-scale power suppression was confirmed as a real feature of the data. The match between the loop quantum cosmology prediction and the observation was noted by researchers in the field as a meaningful agreement, though not a definitive confirmation. It is not proof, proving that the suppression came from a quantum bounce rather than from some other physical process requires additional observations and measurements that future instruments may provide. But the alignment between theory and data is suggestive. And suggestion, in cosmology, is often where the most important stories begin. The Big Bounce resolved something that had troubled cosmologists since the first quantum gravity calculations were applied to the early universe. In classical general relativity and in the standard quantum cosmology that preceded loop quantum cosmology, the question of initial conditions was simply deferred. The model was initialized at some very early moment with whatever conditions produced the universe we observe, and no attempt was made to explain those initial conditions from first principles. The Big Bounce changes this. In loop quantum cosmology, the initial conditions of our universe are determined by the physical state of the previous contracting universe at the moment of maximum compression. They are not arbitrary. They follow from the physics of the bounce, and this is a specific and potentially testable prediction about why the universe has the initial conditions it has. There is a story behind the cyclic universe that begins not with mathematics but with disillusionment. Paul Steinhardt of Princeton University spent the better part of 2 decades as one of the founding architects of inflationary cosmology. He was present at the birth of the idea, contributed to its early theoretical development, and watched it become the consensus framework of early universe cosmology. Inflation solved real problems: the flatness problem, the horizon problem, the relic problem. It explained why the observable universe looks so uniform and geometrically flat. It gave a natural mechanism for generating the small density fluctuations that seeded cosmic structure. For many years, Steinhardt believed in it completely. But as the field matured and observations accumulated, something began to trouble him. The theory had to be revised repeatedly to stay consistent with data. Every new measurement that came in revealing something inflation had not originally predicted was met with a new variant of inflation, carefully engineered to accommodate the new result. The original models spawned new inflation, which spawned chaotic inflation, which spawned eternal inflation, which spawned a zoo of variants with different scalar fields, different potentials, different initial conditions, each one designed to survive the latest data, and each one adding new free parameters to maintain agreement with observations. It's really hard to think of a historical example where that actually led to what turns out to be the right answer, Steinhardt said. Almost always, that's a sign that the Titanic is sinking. He did not abandon the field. He concluded that the framework was wrong in some fundamental way and began building an alternative, one that would explain the same cosmological observations without the perpetual patchwork of inflation's growing family of models. The theory he arrived at would require him to reach into the most exotic corners of string theory, to rethink the nature of the Big Bang, and ultimately to propose that the universe has been cycling through creation and destruction for longer than any human concept of time can encompass. The question of what the pre-Big Bang universe looked like in loop quantum cosmology has been addressed in several research programs by Ashtekar and his collaborators. The overall conclusion is that the previous universe was, in its large-scale properties, very similar to our own. It was expanding, it contained matter and radiation, and it was governed by the same fundamental physical laws. The differences between the pre-Big Bang universe and our universe arise primarily from the details of how the quantum bounce transformed the quantum state. These differences are precisely what leave the signatures in our CMB that loop quantum cosmology predicts, and that observers are actively trying to measure with the next generation of instruments. The theoretical framework Steinhardt reached for was built on an idea that string theory introduced into physics and that has no equivalent in ordinary experience. String theory requires extra dimensions of space. Our universe of 3 spatial dimensions and 1 of time is embedded in a richer geometry that contains additional spatial dimensions, curled up at scales so small that no existing instrument can detect them. The existence of these extra dimensions is required by the mathematics of string theory for the equations to remain consistent, and in the fully extended formulation called M-theory, these dimensions have a specific physical interpretation. Our universe is a 3-dimensional brain, a membrane-like surface, suspended in a higher dimensional space. Everything we can observe, every star, every galaxy, every particle of matter, exists on the surface of this brain. The brain extends in our 3 dimensions of space without any limit that we have found. And in the higher dimensional space, beyond it, separated by a gap that is smaller than the width of a proton, when measured through the extra dimension, is a second brain, a parallel universe floating close to ours but in a direction we cannot perceive or move in. Gravity can cross this gap. Unlike the other forces, gravity propagates through extra dimensions, and it acts across the tiny higher dimensional gulf between the 2 brains. It slowly pulls them toward each other through a dimension we cannot experience. Over an enormously long time, this gravitational attraction brings the 2 brains together. When they collide, the kinetic energy of their approach is released as heat and matter on the surface of each brain. The universe fills with radiation. The temperature spikes. Particles condense from the energy of impact. What we call the Big Bang was not a creation event. It was a collision. Steinhardt's critique of inflation eventually found a mathematical formulation that captured what had been troubling him. In a rigorous analysis of the full space of possible initial conditions for inflation, he and his colleagues showed that inflation is not a generic outcome of a universe starting with a random initial state. Instead, inflation requires very specific initial conditions that are themselves highly improbable in the space of all possible starting configurations. This is the measure problem of inflation. The fine-tuning required to start inflation is at least as severe as the fine-tuning problems that inflation was supposed to solve. The Titanic, Steinhardt concluded, had been sinking the whole time, and the proposed lifeboats faced the same structural weakness. After the collision, the 2 brains recoil and spring apart. The new universe that has been created by the impact expands and cools. Over billions of years, matter condenses into atoms. Atoms assemble into gas clouds. Gas clouds collapse under gravity into stars. Stars forge heavy elements in their cores and scatter them in their deaths. And those elements combine into planets and into life and into civilizations capable of asking where they came from. The expansion continues, driven by the dark energy that was seeded by the collision. Galaxies draw apart. The cosmic web stretches and thins. The last stars exhaust their fuel and cool to dark remnants. The last gravitationally bound structures dissolve. The universe empties over a timescale that makes the current age of the universe look like an instant. And then something happens that the standard model of cosmology does not predict and cannot explain. The attractive force between the brains, operating through the extra dimension, begins to overcome the dark energy driving expansion. The brains, which have been moving apart since the last collision, slowly decelerate, halt, and begin falling back toward each other. The contraction builds over roughly 1 trillion years. As the brains approach again, their surfaces wrinkle under quantum fluctuations, the same quantum fluctuations that made the previous collision uneven and that seeded the structure of the previous universe. The wrinkles grow. Different regions of the brain surfaces make contact at slightly different times. The energy of the approach is converted into heat and radiation, and matter at each contact point. Another Big Bang erupts across the surfaces. Another universe is born. This cycle has no beginning. The membranes have been colliding and separating forever, each collision creating a universe, each universe living out its full trillion-year lifespan, each death setting up the next birth. There was no first collision. Our Big Bang was not the first. It was simply the most recent, and the specific conditions of our universe, the precise pattern of its initial fluctuations, and the particular values of its cosmological parameters were shaped by events in the previous cycle that we can never directly observe, but whose signatures may still be readable in the oldest light we have. The observational test that most directly distinguishes the ekpyrotic model from standard inflation concerns primordial gravitational waves. Inflation generates a background of gravitational waves with a characteristic spectrum. The ekpyrotic model predicts an essentially undetectable gravitational wave background. Several experiments, including the BICEP telescopes at the South Pole and the Planck satellite, have searched for the primordial gravitational wave background. So far, no detection has been made, and the upper limits are approaching the range where a standard inflationary signal should be visible if inflation occurred. The absence of detection is consistent with the ekpyrotic model and increasingly constraining for many versions of inflation. The next generation of instruments will either detect the signal or push the upper limit below any plausible inflationary prediction. The test of the ekpyrotic model against inflation will not wait indefinitely. The Simons Observatory in Chile, the BICEP array at the South Pole, and eventually the CMB Stage 4 experiment will collectively push the sensitivity to primordial gravitational waves far below any plausible inflationary signal. If those experiments detect nothing, the standard inflationary models that predict a detectable background will be ruled out, and the ekpyrotic model will be strongly favored. If they detect the gravitational wave background at the level predicted by inflation, the ekpyrotic model will be severely constrained. The confrontation between these two frameworks is coming, and within the next decade or two, cosmology will have a clear answer to which one better describes the physics of our universe's origin. The ekpyrotic cycle arrives at a conclusion that sounds deceptively simple and turns out to be philosophically staggering. If the two brains have been colliding forever, with no first collision, then there has never been a moment when the universe did not exist in some form. Our Big Bang had a predecessor. That predecessor had a predecessor before it. Pull on the thread of this universe, and you find it connected to an endless chain of universes stretching backward through time without a first link. This contradicts the most basic assumption that cosmology carried for most of its history, that the Big Bang was a genuine beginning, that before it there was nothing, not empty space, not darkness, not even time. In the standard model, the question of what preceded the Big Bang was not unanswered, it was meaningless. The universe began. Beginning was something that happened only once. In the ekpyrotic model, beginning is not a concept that applies. The universe has always been, in one form or another, cycling through expansions and contractions and collisions without any original instance. Some physicists find this deeply unsatisfying. They traded one mystery for another. Instead of a mysterious beginning from nothing, the cyclic model offers an eternal process that runs without any apparent reason and without any explanation for why the cycling started. Others find it more coherent than the alternative. The cycling universe requires no external cause, no moment of creation, no agent to set the first conditions. It is self-sustaining and self-perpetuating, a physical system that has been generating its own conditions for as long as conditions have existed. But the deepest question that the cyclic model raises is not about whether the cycle started or not. It is about what determines the laws that govern the cycling. Why are the fundamental constants of physics, the strength of gravity, the mass of the electron, the speed of light, the value of the cosmological constant, the specific values they are? In an eternal cycling cosmos with no designer and no first moment, those values must somehow emerge from the dynamics of the cycle itself. That answer has not yet been found, and finding it would be one of the most significant accomplishments in the history of physics. The cyclic model's answer to the origin problem is philosophically significant in a way that goes beyond the scientific content. Most scientific theories that address the origin of the universe either postulate a beginning, leaving open the question of what caused it, or propose an eternal background, leaving open the question of where that background came from. The cyclic model says the universe's existence requires no first cause and no external explanation because the universe has never not existed. There was always a brain, always a cycle, always a physical process generating new Big Bangs. The existence of the universe is not a problem to be explained by something outside it. It is simply the state of affairs that has always been and will always be the case. Of all the implications that follow from bouncing and cyclic cosmologies, the one that reaches deepest into both science and philosophy is the question of information. In the standard model of the Big Bang, the origin singularity functions as a wall that information cannot cross. Whatever state the universe was in before the Big Bang, if there was a before, was destroyed at the singularity and replaced by the initial conditions of the new universe, which emerged without memory of any prior state. The beginning was genuinely blank, a clean slate with no connection to anything before it. In loop quantum cosmology and in the ekpyrotic model, this picture is explicitly replaced. In loop quantum cosmology, the quantum bounce is a physical process governed by the continuous equations of quantum mechanics, which require information to be conserved. The quantum state of the universe at the moment of maximum compression, the state that existed at the bounce point, maps directly onto the quantum state of the universe that emerges in the expanding phase that follows. Every correlation, every pattern, every statistical relationship between fluctuations that was present in the contracting universe is transformed but not destroyed by the bounce. In the ekpyrotic model, the brain collision that constitutes the Big Bang is likewise a physical process, and physical processes conserve information. The specific pattern of wrinkles on the brain surface at the moment of impact, which determines the distribution of density variations that seed the structure of the new universe, is determined by the quantum state of the brains at the end of the previous cycle. The universe that emerges from the collision inherits information from the universe that preceded the collision. The implication is profound. Right now, in this universe, the large-scale distribution of matter and the specific statistical properties of the CMB temperature fluctuations may be encoding information about events that occurred in a cosmos that no longer exists. The first galaxies to form, the specific way the cosmic web assembled, the statistical properties of the gravitational wave background. All of these may carry in their structure the fingerprints of a previous universe. We are, in a very literal, physical sense, reading the history of a universe we cannot visit every time we analyze the structure of our own. The specific kinds of information that survive a bouncing transition depend on the dynamics of the bounce. In loop quantum cosmology, quantum correlations between different spatial regions are the primary carriers of information through the bounce. These correlations show up in the statistical properties of fluctuations, in the way temperature variations, at different points on the CMB sky, are correlated with each other across different angular scales. Measuring these correlations with precision is one of the primary goals of next-generation CMB experiments. A specific pattern of correlations, one that matches the predictions of the quantum bounce rather than standard inflation, would be compelling evidence that information from a previous universe is encoded in our oldest light. Roger Penrose, Oxford mathematician and Nobel laureate, came to the problem of the pre-Big Bang universe from a direction that had not been taken before. He was not asking what state preceded the Big Bang by working backward from our current universe. He was asking what the laws of physics demand must be true about the very far future of the universe, and then asking what that future has to do with the very far past. What he found was a deep structural connection that most physicists had not noticed, and it led him to a picture of cosmic history that is simultaneously more elegant and more vertiginous than any cyclic model built on brains or bounces. Consider what happens to the universe in the far future, on timescales that make the current age of the cosmos look like an instant. The last stars exhaust their nuclear fuel over the course of trillions of years, and cool to dark, dense remnants. White dwarfs, neutron stars, and black holes inherit the mass of dead stellar populations. Galaxies slowly disassemble as gravitational interactions, scatter their stars into the surrounding void, or funnel them into central black holes over many trillions of years more. Eventually, in a cosmos dominated by dark energy and expanding forever, even the last gravitationally bound structures dissolve. The black holes themselves evaporate. Stephen Hawking showed in the 1970s that black holes are not perfectly black. Quantum mechanics near the event horizon allows particle-antiparticle pairs to form, with one particle falling in and one escaping. Over time, this process drains the black hole's mass and converts it into a thin trickle of radiation. The most massive black holes in the universe, billions of times more massive than our star, would take unimaginably long to fully evaporate, but eventually even they disappear. When all the black holes are gone, what remains is a universe of photons and a few massless particles expanding endlessly in an enormous and empty space-time. There is no mass, there is no scale, there is no structure. Penrose looked at this state and recognized it. A universe with no mass, governed by conformally invariant physics, has a profound mathematical property that he would use to connect the end of one aeon to the beginning of the next. Penrose's path to conformal cyclic cosmology was shaped by his deep engagement with the second law of thermodynamics. For Penrose, the most profound puzzle about the universe is not the Big Bang itself, but the extraordinarily low entropy of the initial state that the Big Bang emerged from. The universe we observe, with its galaxies and stars and complex structures, is in a state of vastly higher entropy than the early universe was. But the early universe was itself in a state far from maximum entropy. Why was the Big Bang not in thermal equilibrium? This puzzle, which Penrose called the whale curvature hypothesis problem, led him to investigate what kind of pre-Big Bang state could explain the astonishing improbability of our universe's initial conditions. The connection that Penrose found between the end of one universe and the beginning of the next relies on a class of mathematical transformations called conformal rescalings. A conformal transformation preserves the angles between curves in spacetime and preserves the causal structure, the pattern of which events can influence which other events, while changing the overall scale of distances and times. Under conformal rescalings, the very small can be made the same as the very large if they share the same conformal geometry. Penrose's insight was that the conditions at the infinitely remote future of a dead, massless, conformally invariant universe are conformally equivalent to the conditions at the beginning of a new Big Bang. The infinite expanse of the dying universe, stretched across an unimaginable volume of empty spacetime, can be conformally compressed onto the infinitesimally small initial surface of a new cosmos. The death of one aeon and the birth of the next are the same physical event, described at different scales. In this framework, there is no gap between consecutive aeons. The end of one universe seamlessly becomes the beginning of another without any intervening void and without any moment where nothing exists. Time does not restart. Causality is not broken. The conformal transformation carries the physical state of the dying universe forward into the living universe that follows. Our Big Bang was not a creation. It was a conformal transformation applied to the ending state of a previous cosmos. Penrose calls each universe an eon. The aeons form an infinite sequence, each one complete in itself, each one conformally connected to the next. Our aeon had a predecessor and will have a successor. The predecessor had its own predecessor. The sequence has no first member and no last member. It runs in both directions without beginning and without end. The conformal transformation connecting one aeon to the next goes deeper than a mathematical device. It reflects a deep physical reality about what happens when mass disappears. The parameter that distinguishes massive from massless objects is time itself. Massive particles have rest mass and therefore carry an intrinsic clock that defines a natural timescale. Massless particles like photons do not. When the universe loses all mass, it loses all intrinsic clocks. There is no longer any physical way to distinguish between different scales of distance or time. A universe that is conformally invariant at its beginning and at its end can be connected through a conformal transformation that maps one onto the other, with physical signals from the ending state appearing as specific features in the beginning state of the next eon. Penrose's conformal cyclic cosmology makes a specific and testable observational prediction, which elevates it from pure mathematical speculation to scientific hypothesis. The physical events that happened in the previous aeon leave traces that survive the conformal transition and appear as detectable features in the cosmic microwave background of the new aeon. The key events are the deaths of the last great black holes. In the previous aeon, after all ordinary matter had been consumed or dispersed, the final objects to persist were the most massive black holes. These leviathans evaporated slowly through Hawking radiation over incomprehensibly long timescales, their mass converting to radiation with each passing era. As each one approached its final moments, the evaporation accelerated and concluded in a terminal burst of concentrated radiation from a small spatial region. That burst released the last energy of an object that may have been more massive than billions of ordinary stars. Through the conformal rescaling that connects one aeon to the next, these terminal Hawking radiation bursts were compressed and transformed. What was originally a burst of radiation spread across a region of space in the dying aeon becomes, after the conformal transformation, a concentrated spot of elevated temperature in the CMB of the new aeon. Each evaporating black hole in the previous aeon should produce one such spot, a small circular region in the CMB map where the temperature is detectably above average. Penrose called these Hawking points, in honor of the physicist whose theoretical discovery of black hole evaporation provides the physical basis for the prediction. In 2020, Penrose and colleagues published a paper claiming to have found exactly these Hawking points in the Planck and WMAP satellite data. They reported circular hotspots appearing in both datasets at the same sky locations, with a statistical significance they assessed at far above what would be expected from chance. The paper represented one of the most provocative observational claims in the history of modern cosmology. The Hawking points prediction is one of the most specific and detailed observational claims to emerge from any pre-Big Bang theory. Penrose and his collaborators did not simply predict that some anomaly should exist in the CMB. They predicted a specific kind of anomaly, circular regions of elevated temperature with a specific range of angular sizes, appearing at locations corresponding to specific events in the previous aeon. The angular sizes predicted correspond to the geometry of the conformal transformation. The temperature amplitudes depend on the masses of the evaporating black holes and the rate of the conformal rescaling. This level of specificity is what separates a scientific prediction from a vague claim, and it is what makes the debate about whether Hawking points are present in the data scientifically meaningful rather than philosophical. The scientific community's response to the Hawking points paper was immediate, intense, and far from unanimous. This is worth understanding in some detail, because the controversy around the Hawking points claim illustrates something important about how science actually works when the question being asked is at the absolute edge of what current instruments can resolve. Within months of the paper's publication, multiple independent research groups downloaded the Planck and WMAP data and ran their own analyses. Some found results broadly consistent with the Penrose team's claims. Others found the claimed signal to be far weaker than advertised, or to disappear entirely when different statistical methods were applied. In 2020, a team at the University of British Columbia reported that the evidence for Hawking points was present at only 87% confidence using their statistical approach, a number that, in particle physics, would not even rise to the level of a marginal hint. More challenging still was a study from the University of California at Santa Barbara, whose team built a machine learning tool specifically designed to search for the circular temperature patterns Penrose predicted. They called it HawkingNet. When they applied it to the highest resolution Planck data, they found that certain spurious features in the raw data, individual pixels of unusual brightness or darkness, that arose from measurement artifacts rather than genuine cosmological signals, were producing false positive clusters that looked like Hawking points when older search methods were applied. After removing these artifacts, the evidence for Hawking points became statistically insignificant. The current situation is a genuine scientific impasse. The Penrose team and its critics use the same data and reach opposite conclusions. The resolution will require CMB observations of higher resolution and lower noise than any currently available instrument can provide. The CMB Stage 4 experiment and the Lightbird satellite, both planned for the coming decade, will provide exactly that. The Hawking points debate is not closed. It is waiting for better instruments to settle it. The debate about Hawking points illuminates a general challenge in observational cosmology, distinguishing genuine physical signals from noise and artifacts in data that is already extraordinarily faint. Even the most precise CMB measurements are limited by detector sensitivity, astrophysical foreground contamination, and the finite number of photons available. At the level of precision required to detect or rule out Hawking points, every artifact in the data matters. Every systematic error, every imperfectly subtracted foreground, every statistical choice about how to analyze the temperature distribution affects the conclusion. The honest assessment is that the evidence is currently ambiguous, and resolving that ambiguity requires better instruments rather than better analysis of the existing data. The pre-Big Bang frameworks explored so far, loop quantum cosmology, the ekpyrotic scenario, and Penrose's conformal cyclic cosmology, all share a common structural feature. The universe that preceded ours existed on the same cosmological timeline as our own before the Big Bang in time, connected to our universe through a physical transition. But a proposal by Latham Boyle at the Higgs Center for Theoretical Physics at the University of Edinburgh challenges even this assumption, suggesting that the companion to our universe is not a predecessor in time, but a simultaneous twin running in the opposite direction. In Boyle's CPT symmetric model, the Big Bang is a point of exact symmetry. The universe does not begin there and proceed in one direction of time. Instead, the Big Bang is a nexus where two arrows of time meet. Imagine two ice cream cones touching precisely at their tips. One cone represents our universe, with time running from the Big Bang forward into the expanding future. The other cone represents a mirror universe, with time running from the Big Bang backward in the opposite temporal direction. The universe in the other cone is not our universe viewed in a historical mirror. It is a genuine physical twin with reversed properties. Matter is replaced by antimatter. Left-handedness is replaced by right-handedness in particle interactions. The arrow of entropy and thermodynamics runs opposite to ours. From our perspective, the other universe is entirely in our past, moving away from the Big Bang in the only direction we can experience as time. From the perspective of any observer in the other universe, our universe is entirely in their past. The CPT symmetric structure has an important physical consequence. One of the deepest unsolved mysteries of cosmology is why our universe contains matter rather than being an equal mixture of matter and antimatter that would have annihilated into pure radiation at the Big Bang. In Boyle's model, the two-lobed universe is globally neutral. Our lobe has matter. The mirror lobe has antimatter. The total is zero. The asymmetry in our lobe is not a mystery that needs special explanation. It is the necessary consequence of the structure of a CPT symmetric universe. The CPT symmetric model has an important prediction that follows directly from the structure of the theory. Because the Big Bang in this model is a point of exact symmetry rather than a directional creation event, the quantum state at the Big Bang does not naturally generate the kind of time-asymmetric gravitational wave background that inflationary models predict. In the CPT symmetric universe, the two lobes of the universe together form a system with zero net CPT charge, and the initial conditions at the Big Bang reflect this symmetry. If gravitational wave detectors eventually confirm a primordial background at the inflationary level, Boyle's model is ruled out. The search for primordial gravitational waves is therefore also a test of whether the universe has a symmetric twin running backward through time. All of the models that posit an eternal or a cyclic past, a universe or sequence of universes extending infinitely backward in time, run headlong into a mathematical theorem that has become one of the most discussed and most contested results in modern cosmology. The theorem was proved in 2003 by three physicists: Arvind Borde, a physicist at Long Island University; Alan Guth, the architect of inflationary cosmology at the Massachusetts Institute of Technology; and Alexander Vilenkin at Tufts University. Together, the BGV theorem states that any spacetime which has been, on average, expanding throughout its history cannot be extended infinitely into the past. The mathematical argument behind the theorem is not based on specific assumptions about the kind of matter or energy filling the universe, or about whether general relativity is exactly correct. It is based on the behavior of geodesics, the paths traced by objects moving freely through spacetime, and it holds under very general geometric conditions. Any universe with a positive average expansion rate along any family of path-directed geodesics must reach a boundary in the past. The expansion cannot have been going on forever. For eternal inflation, this is immediately devastating. The inflating background that drives the creation of bubble universes has been expanding, on average, throughout its history. Therefore, by the BGV theorem, it cannot have been eternally expanding in the past. It must have had a beginning, even if it is eternal into the future. Vilenkin has been explicit and public about this conclusion. At a major cosmological conference in 2012, he announced, "All the evidence we have says that the universe had a beginning." He has since reinforced this position in multiple publications, noting that no viable model of an eternally existing universe without a beginning has been constructed, and the BGV theorem provides reason to believe none can be. The full force of the BGV theorem becomes clear when applied to the most ambitious eternal inflation models. In chaotic eternal inflation, the most theoretically elaborate inflationary framework, inflation is supposed to be eternal in both directions, having been happening forever in the past and forever in the future. The BGV theorem rules this out. If the inflating background has been expanding on average, its past history is finite. There must have been a first moment of inflation, which means there must have been something before inflation. That something before inflation is precisely what the theorem refuses to describe. The theorem identifies a wall. It does not tell you what is on the other side of the wall. That is where the theoretical work of building pre-Big Bang cosmologies becomes necessary. The BGV theorem has not gone unchallenged. The physicists it most directly threatens have worked hard to find ways around it, both by challenging its mathematical assumptions and by constructing explicit models of cosmological spacetimes that appear to evade its implications. Alan Guth, one of the theorem's authors, has argued that the theorem applies to classical spacetime descriptions and may not hold when quantum gravity effects are taken into account. Near any past boundary identified by the theorem, the universe would be in a regime of extremely high energy density, where quantum effects on spacetime geometry become dominant, and the classical geodesics on which the theorem's argument relies would not be well defined. In a full quantum gravity theory, the notion of average expansion rate along a classical geodesic might not have the same meaning as in classical general relativity, and the theorem's conclusion might not follow. Guth has supported models that attempt to construct spacetimes with no classical beginning. Carroll and Jenny Chen built a model in which a time-symmetric spacetime, symmetric about a moment of minimum size, spontaneously spawns inflating regions. The universe in this picture has no boundary in the classical sense. On one side of the symmetric moment, time runs forward and the universe expands. On the other side, time runs backward and the universe also expands, away from the symmetric moment in the opposite temporal direction. Vilenkin has argued that this model does not genuinely evade a beginning. because the reversal of the time direction itself constitutes a physical starting point in any meaningful sense. The debate continues, without resolution. What both sides agree on is the stakes. The question of whether the universe had a beginning is one of the most fundamental questions in all of cosmology, and the BGV theorem has forced it to be asked with unprecedented precision. The scientific community's response to the BGV theorem divided roughly along two lines. One group accepted the conclusions and treated the past boundary of eternal inflation as a genuine beginning, requiring a physical explanation, whether through quantum tunneling, a no-boundary wave function, or some other mechanism. The other group, including Guth himself, argued that the theorem applies only to classical spacetime, and that quantum gravity corrections will modify the picture. In a full quantum gravity theory, the concept of average expansion along a classical geodesic may not be well defined near the Planck scale, and the theorem's constraint may not survive into the quantum regime. Both positions are held by technically skilled researchers making reasonable arguments from incomplete evidence. The resolution awaits a confirmed theory of quantum gravity to move beyond the constraints of the BGV theorem, or to provide the physics that exists at any past boundary the theorem identifies. You need a theory that extends beyond classical general relativity into the regime of quantum gravity. String theory, the most extensively developed candidate for such a theory, brings with it a feature that has enormous cosmological consequences: the landscape of possible physical universes. String theory requires extra spatial dimensions, curled up at scales far below anything current technology can probe. Each of these extra dimensions can be configured in different ways, and each configuration corresponds to a different effective theory with different physical constants, different particle masses, and different force strengths. The number of distinct possible configurations is enormous, with estimates hovering around 10 to the power of 500, a number that is effectively infinite for any practical purpose. Each configuration corresponds to a different possible universe, with its own set of physical laws governing everything within it. The concept that all of these configurations are physically realized somewhere in an eternally inflating multiverse is called the string landscape. Leonard Susskind of Stanford University developed this idea most influentially, arguing that string theory should be understood not as a theory that predicts a unique universe with unique physical constants, but as a theory that predicts an ensemble of universes, each with the constants corresponding to one configuration of the extra dimensions. Our universe inhabits one specific configuration among 10 to the 500th. The constants we measure, the strengths of the forces, and the masses of the particles, reflect the particular way the extra dimensions are curled up in our bubble universe. In the vast majority of other bubbles, the constants are different, and the resulting physics does not permit the formation of atoms, stars, galaxies, or any complex structure. The specific constants of our universe are not privileged. They are simply the constants that allow us to exist and ask about them. The string landscape raises a question that penetrates to the foundations of science itself. If string theory generates an enormous number of possible vacua, each corresponding to different physics, and we have no theoretical mechanism to select our specific vacuum over any other, then string theory cannot predict the physical constants we measure. It can only say that we observe constants compatible with our existence. Many physicists find this deeply troubling because prediction from first principles has been the gold standard of scientific achievement since the era of Newton and Maxwell. A framework that explains fine-tuning through selection rather than through dynamics may represent a fundamental boundary of what physics can explain, a limit below which the deeper question of why these constants rather than others simply has no answer within physics. The mechanism that transforms the abstract landscape of possible string configurations into the concrete physical reality of a multiverse is eternal inflation. If eternal inflation is real, if some region of space-time is always inflating, then quantum fluctuations in the inflating background will continually nucleate new bubble universes. Each nucleating bubble adopts the physical constants corresponding to whatever string configuration it lands on as it drops out of the inflating background. Over the infinite history of the eternally inflating background, every configuration in the landscape is realized in some bubble, an infinite number of times. Our Big Bang was one such nucleation event. A quantum fluctuation in the inflating background caused a tiny region to drop into the lowest energy vacuum state corresponding to our particular set of physical constants. That tiny bubble inflated from the inside into the vast universe we inhabit. Meanwhile, outside our bubble and completely inaccessible to us, the inflating background continued generating new bubbles, new universes, each with its own constants and its own history of structure formation, or its own rapid collapse into nothing, or its own instantaneous expansion into an empty void. The existence of these other bubbles cannot be tested directly. No signal can cross from one bubble universe to another at speeds consistent with the causal structure of either. We are permanently isolated in our bubble, unable to confirm or deny by any direct observation whether the landscape and its multiverse are real. What eternal inflation can offer is a framework for understanding why our constants have the values they do, and a context in which the existence of our universe requires no singular creation event and no special mechanism. In the eternal inflation landscape, universes are inevitable. They arise from the physics of the background, constantly and without end. The terrifying implication of this picture is not that other universes exist. It is that our universe is not special. It is one of an infinite number of realizations of one configuration out of 10 to the 500th possibilities, in a background that has been inflating for an eternity without beginning or end in either direction that matters to our existence. The silence around our bubble universe is one of the most profound constraints on cosmological knowledge. In eternal inflation, the bubble universes produced before ours are causally inaccessible. No signal can reach us from any predecessor bubble. We cannot confirm their existence by any direct measurement. What we can test is whether our own universe carries any marks of its nucleation event, any scars from the bubble wall forming around us, or any signatures in the CMB from the specific quantum state of the inflating background at the moment our bubble formed. These signatures, if they exist, would be subtle and specific, requiring the next generation of CMB instruments to detect. Their absence would not disprove eternal inflation, but would continue to push it into the territory of unfalsifiable hypothesis. The eternal inflation framework, whatever its relationship to the ultimate structure of reality turns out to be, has had a profound effect on how physicists think about the relationship between physical law and physical existence. Before eternal inflation, it seemed natural to ask why the universe has the specific physical constants it does, as if those constants were facts about a unique universe that could have been otherwise but somehow were not. Eternal inflation and the landscape make that question more specific. Our constants are the constants of our particular bubble, and the question of why these constants, rather than others, becomes the question of why we find ourselves in this bubble rather than another one. That is an anthropic question, a question about observers and observation, rather than a question about uniqueness and necessity. In an infinite, eternal cosmos, one of the oldest and most unsettling thought experiments in physics becomes unavoidably real. The Boltzmann brain paradox takes its name from Ludwig Boltzmann, the 19th century Austrian physicist who established the statistical foundations of thermodynamics. Boltzmann understood that the laws of thermodynamics are not absolute prohibitions, but probabilistic statements. Given enough time and enough matter, any configuration that is physically possible will eventually occur, however improbable it might seem. In an eternally inflating multiverse, or in an infinite cyclic cosmos, the implications of this principle become catastrophic for the concept of rational observation. Consider what you are: a brain, an extraordinarily complex arrangement of matter that arose through 4 billion years of biological evolution, embedded in a solar system that formed over 4.5 billion years. in a galaxy that assembled over 10 billion years, in a universe that has been evolving for nearly 14 billion years. The probability of all these processes combining to produce exactly you, with your memories and your consciousness, is almost incomprehensibly small. But in an infinite or eternal cosmos, there is another way to produce a mind with your particular memories and experiences: pure thermal or quantum fluctuation. Random fluctuations in a heat bath can spontaneously assemble any configuration of matter, including a brain with whatever memories you happen to have right now, surrounded by nothing, having a single moment of experience before dissolving back into the chaos it came from. This fluctuating brain is called a Boltzmann brain, and the probability of one forming by fluctuation is vastly higher than the probability of an entire universe forming, a galaxy evolving, a star forming, a planet developing life, and that life evolving complexity over billions of years. In any model of cosmology that allows an infinite amount of time and space, Boltzmann brains should vastly outnumber genuine evolved observers. If that is true, then any given observer, including you right now, is far more likely to be a Boltzmann brain with false memories than a genuine evolved being. The standard models of cosmology, when they imply infinite cosmological volumes, produce this paradox automatically. Every serious cosmological theory must grapple with it and find a way to suppress the formation of Boltzmann brains relative to genuine observers, or it fails on its own terms. The solutions proposed to the Boltzmann brain problem shape the kinds of pre-Big Bang cosmologies that can be considered viable. Any model of the pre-Big Bang universe that leads to infinite volumes and infinite times must explain why observers like us are typical rather than exceptional. This constraint is one of the most powerful filters in modern theoretical cosmology, and it eliminates many otherwise attractive scenarios. The Boltzmann brain problem is not merely philosophical, it has practical consequences for how cosmological theories are evaluated. A theory that predicts more Boltzmann brains than genuine evolved observers has predicted that any given observer is more likely to be a momentary fluctuation with false memories than a genuine being. This makes the theory unreliable on its own terms. Several proposed resolutions require modifying the cosmological history so that the universe either terminates or resets before enough time passes for Boltzmann brains to form at rates exceeding genuine observer formation. In eternal or cyclic models with infinite cosmic history, this constraint is genuinely difficult to satisfy, and it forces serious modifications to the simplest eternal inflation pictures. In December of 2021, the most expensive and ambitious scientific instrument ever built was launched from a spaceport in French Guiana and sent to a gravitational balance point 1 million miles from Earth. The James Webb Space Telescope was the culmination of 3 decades of planning, engineering, and international collaboration, and its primary scientific mission included observing the very early universe to test our models of how the first galaxies formed. The first results began arriving within months of the telescope reaching its destination and achieving operational status. What the data showed immediately caught cosmologists off guard. Galaxies that were fully assembled, more massive than any model had predicted for the epoch in which they were observed, appeared within the first few 100 million years after the Big Bang. These were not the small, irregular protogalaxies that models suggested should be the first structures to form. They were large, well-organized, chemically enriched systems that looked, in many ways, more like mature modern galaxies than like infant ones. The standard model of galaxy formation is hierarchical. Small density fluctuations in the early universe collapse under gravity into small halos of dark matter, which attract gas and form small galaxies. Those small galaxies then merge over billions of years into larger ones. The largest galaxies, comparable to the Milky Way, should take several billion years to assemble in this framework. Finding galaxies of comparable mass already fully formed within the first billion years of cosmic history was, as one of the telescope's original architects put it, a genuine conundrum. explanations began circulating immediately. Some researchers argued that early galaxies simply formed stars more efficiently than later ones, converting gas to stellar mass at rates that standard models had not predicted. Others suggested that the light contributions from central black holes in these early galaxies had been misattributed to stellar mass, making the galaxies appear more massive than they actually were. Both of these effects may be real, and both may account for some of the discrepancy. But some outlier cases refuse to yield to any proposed explanation, and the scientific debate remains active. The most provocative proposals suggest that the anomaly points toward conditions in the pre-inflationary or even pre-Big Bang universe that seeded structure formation earlier than the standard timeline allows. If the initial conditions of our universe were shaped by a predecessor, if the quantum bounce or the brain collision that produced our Big Bang introduced specific patterns of density enhancement that are not present in standard inflationary models, then some galaxies might have formed earlier than the standard timeline predicts, because they started with a head start written into the initial conditions by a previous cosmic history. The initial reaction of cosmologists to the first Webb results included both excitement and caution. Caution because the initial analyses relied on photometric redshifts estimated from the color of light rather than spectroscopic conformations, which carry significant uncertainties. Some apparently massive early galaxies might be closer, less massive objects misidentified at first. But as spectroscopic follow-up observations accumulated, the most anomalous objects held up. The most extreme cases were confirmed as genuinely being at the distances and epochs their initial photometry suggested. The anomaly did not go away with better data. The galaxies that should not exist, by the logic of the standard model, are still there, waiting for an explanation that standard cosmology has not yet provided. In November of 2024, an international team of astronomers published findings that deepened the challenge posed by early galaxies significantly. Using the James Webb Space Telescope's powerful spectroscopic capability, which can identify the specific light wavelengths emitted and absorbed by different chemical elements in distant objects, the team confirmed the existence of 3 galaxies at very early cosmic epochs, whose stellar masses were comparable to that of the entire Milky Way. The spectroscopic analysis was not an estimate or an inference from brightness. It was a direct measurement of specific elemental signatures, particularly oxygen emission lines that can only be produced by stars that have already lived out their lifetimes, fused lighter elements into heavier ones through nuclear burning, and then scattered those elements into the surrounding galaxy through stellar winds and supernova explosions. The presence of oxygen lines in galaxies from the first billion years of cosmic history meant that multiple generations of massive stars had already formed, burned, and died in these galaxies before the universe was even 10% of its current age. One of the paper's co-authors, Garth Illingworth, at the University of California at Santa Cruz, who had spent more than 3 decades contributing to the design and development of the telescope that made these observations possible, described the findings plainly. The existence of such massive galaxies at the earliest times poses a real conundrum. He did not mean this as rhetorical flourish. He meant that the observation is not comfortably accommodated by any existing model of galaxy formation. The broader significance is that the James Webb Space Telescope was specifically designed to test our cosmological models by observing the early universe with unprecedented sensitivity. Its early results have been a mixed verdict. Many observations confirm the standard model, but a persistent tale of anomalously massive and evolved early systems refuses to be fully explained. The telescope is still operating and will continue to gather data for years. Each new observation has the potential to either resolve the tension or deepen it. The red monster galaxies present a challenge to the standard picture that goes beyond simple abundance. In the standard hierarchical model, large galaxy formation is slowed by feedback from central black holes. As a supermassive black hole grows and consumes gas, it releases enormous amounts of energy in the form of jets and radiation that heat the surrounding gas and shut off star formation. This feedback mechanism is one of the main reasons the largest galaxies are expected to be rare in the early universe. The red monsters seem to have formed without this feedback, operating effectively, building up stellar mass at rates that exceed what any current model predicts. Whether they formed in environments where feedback was less efficient, or whether they represent a fundamentally different physics of early galaxy formation, is one of the most active questions in observational cosmology today. Alongside the puzzles raised by the James Webb Telescope, a different anomaly in cosmology has been building for years and has now reached a level of statistical significance that demands resolution. It concerns a single number, the rate at which the universe is currently expanding. The expansion rate is called the Hubble constant, named for Edwin Hubble, who first demonstrated that distant galaxies are receding from us at speeds proportional to their distances. Measuring the Hubble constant is not simple. Two completely independent methods exist, and they give different answers. The first method uses the cosmic microwave background. By fitting the detailed pattern of temperature fluctuations in the CMB to the best fit model of cosmological evolution and reading off the expansion rate implied by that model, the Planck satellite and its predecessors have produced a value for the Hubble constant that has been refined over decades of increasingly precise measurements. The second method uses the brightness of type Ia supernovae in relatively nearby galaxies. These supernovae are produced when a compact stellar remnant called a white dwarf accumulates enough mass from a binary companion to exceed a critical threshold and explode in a thermonuclear detonation. Because they all detonate at essentially the same mass threshold, they all produce essentially the same intrinsic brightness. Measuring how bright they appear from Earth tells you how far away they are, and comparing that distance to how fast the galaxy containing them is receding tells you the local expansion rate. Decades of observations using this method, conducted by multiple independent teams, have consistently produced a value for the Hubble constant that is roughly 8% higher than the CMB-based value. 8% is not noise. It has survived extensive cross-checking, improvements in the calibration of the distance ladder on which the supernova method relies, and analyses by teams that approach the problem with the goal of finding and eliminating systematic errors. The discrepancy is real, and its persistence has generated the name the Hubble tension in the cosmological community. Some physicists believe the solution will be found in some new physics operating in the early universe, in the period before or during the emergence from the Big Bang, and potentially traceable to conditions that were set by whatever preceded the Big Bang. The Hubble tension has generated an enormous amount of theoretical activity aimed at finding the new physics that could resolve it. Proposals include early dark energy, a form of dark energy that existed in the early universe and decayed before recombination, potentially changing the sound horizon scale that underlies the CMB-based measurement. Other proposals invoke modified gravity theories, decaying dark matter models, or interactions between dark matter and dark energy that operated differently in the early universe than today. Each proposal makes specific predictions about observable quantities beyond the Hubble constant, and each is being tested against the growing body of cosmological data. So far, no single proposal has emerged as clearly superior. The tension remains, and with it the possibility that the resolution requires physics that traces back to the conditions preceding the Big Bang. Before any model of what preceded the Big Bang can gain a foothold in physics, a prior question must be faced with honesty. Can anything come from nothing at all? This is not a naive philosophical question, but a technical one, because quantum mechanics has something specific to say about what nothing actually means. In classical physics, nothing means a state with no energy, no particles, no fields, and no activity. The quantum vacuum is something different. In quantum mechanics, the uncertainty principle forbids any system from simultaneously having zero energy and a perfectly defined state. Even the lowest energy state of a quantum field has a residual energy called the zero-point energy. And it is not quiet. Virtual particle-antiparticle pairs are continuously appearing and annihilating throughout the vacuum, borrowing energy from quantum uncertainty for time intervals so short that they do not violate energy conservation on average. This is not a theoretical nicety. The Casimir effect, a tiny but measurable attractive force between two uncharged metal plates brought close together in a vacuum, arises from virtual particles between the plates being excluded from certain wavelengths that are present outside the plates. The effect has been measured precisely and matches quantum electrodynamics calculations. The quantum vacuum is therefore not nothing. It is an active, fluctuating state, seething with virtual activity. And in the context of quantum gravity, it is even richer. Stephen Hawking and James Hartle proposed in the 1980s that the universe could be understood as a quantum system whose wave function is defined on the space of all possible three-dimensional geometries without any special starting point. In their no-boundary proposal, the universe has no boundary in time. Instead of time being cut off at the Big Bang, it becomes more like a spatial direction near the origin, with no edge. The universe, in this picture, is a self-contained quantum system that does not need a preceding state and does not have a moment of creation. Alexander Vilenkin at Tufts University offered a related but distinct picture. The universe tunneled into existence from a state of zero size through a quantum process similar to radioactive decay. The vacuum from which it emerged was not space and time containing nothing, but rather a mathematical state with no classical space-time at all, a state in which the very framework of space and time emerged quantum mechanically. From this mathematical vacuum, a universe with real space-time appeared through quantum tunneling, inflated rapidly, and became the cosmos we inhabit. No cause was needed in the conventional sense. Because quantum tunneling requires no triggering event, it happens with a certain probability per unit time, and when it happens, it happens. The quantum origin proposals, whether the no-boundary wave function or Vilenkin's tunneling from nothing, share a deep conceptual move that distinguishes them from all classical approaches to cosmology. Both propose that the universe's birth was a quantum event for which the ordinary concept of cause and effect does not apply. In quantum mechanics, events happen without causes. In the classical sense, a radioactive atom decays with a certain probability per unit time, but there is no cause that determines when the decay occurs. The decay happens because it is quantum mechanically allowed. The universe arising from quantum tunneling happens because it is quantum mechanically allowed. No trigger is needed. No preceding state is required. The universe simply arises because arising is a thing that quantum systems that can arise do. All paths in this story converge on a single physical barrier, the Planck scale. At the energy densities and length scales corresponding to the Planck epoch, every confirmed theory of physics breaks down simultaneously, and the only frameworks that can even attempt to describe what happens there are the unconfirmed approaches to quantum gravity. The Planck length, roughly 10 to the negative 35 meters, is smaller than any structure ever probed in particle physics experiments by 17 orders of magnitude. The Planck density, roughly 10 to the 94 grams per cubic centimeter, is so extreme that concentrating that much mass in that small a volume would require energies comparable to the mass energy of the entire observable universe, compressed into a region smaller than a proton. No accelerator, no telescope, no gravitational wave detector, no conceivable technology based on physics as we currently understand it can probe the Planck scale directly. The conditions at the Planck epoch are permanently, perhaps fundamentally, beyond the reach of experiment. The physics that governs the Planck epoch is the physics of quantum gravity, a regime in which space-time itself is subject to quantum uncertainty, and the smooth, classical geometry that underlies all of our current theories ceases to exist. What replaces it, in loop quantum gravity, is a discrete network of quantum links. What replaces it in string theory is a higher dimensional geometry governed by string dynamics. In both cases, The physics is radically different from anything accessible in any laboratory on Earth. This is not simply a practical limitation that better technology might overcome. Some physicists believe it is a fundamental epistemological boundary, a limit set by the physics itself on what can be known about the conditions that produced our universe. If the act of probing any physical system requires concentrating energy at the length scale being probed, and if concentrating that much energy at the Planck scale would spontaneously create a black hole that hides whatever it was producing, then the Planck scale is a horizon of knowability, a permanent limit rather than a temporary one. What we can do is read the CMB, which carries in its faint temperature patterns the imprints of the Planck epoch and potentially of what preceded it, and we can build theoretical frameworks that are internally consistent, that match the large-scale observations we can make, and that make specific predictions about what the next generation of instruments will find. That is where cosmology stands today, pressing hard against a wall it may never fully cross, reading the light on its side of the wall with increasing precision, and inferring what must be on the other side from the patterns the light carries. The Planck scale barrier has spawned a philosophical debate about what it means to do science in a fundamentally inaccessible regime. Some physicists argue that quantum gravity theories are still scientific, even if untestable at the Planck scale, because they make predictions at lower energies that are in principle testable. String theory predicts specific patterns of particle physics that should appear at energies accessible to powerful accelerators. Loop quantum gravity makes CMB predictions. If these lower energy predictions match observations, the theories gain credibility even without direct Planck scale tests. Others argue that a theory untestable at the scale it claims to describe is not fully scientific in the sense that physics has always defined science. This represents a genuine and unresolved methodological challenge for foundational physics. The question of what a universe before ours would actually look like is not merely philosophical in frameworks where pre-Big Bang, physics is governed by the same fundamental laws as our own. In loop quantum cosmology and in the ekpyrotic model, the constants of physics pass through the transition unchanged. The previous universe ran on the same physical rules. Hydrogen and helium were the most abundant elements. Gravity drew matter together into stars. Nuclear fusion processed hydrogen into heavier elements inside those stars. When massive stars died, supernovae scattered those heavier elements into the surrounding gas. Over vast timescales, that enriched gas assembled into new generations of stars, some with planetary systems, some with the conditions that in our universe have given rise to chemistry complex enough to produce life. Whether life arose in the previous universe is entirely unknown. We have no way to know. The previous universe had enough time, enormous amounts of it, for any process that can occur in our universe to occur there as well. If life arose there, it faced the same ultimate fate as life will face in our universe: the eventual darkening and cooling of the cosmos, the death of the last stars, the evaporation of the last black holes. Whether any intelligence in the previous universe was aware that their cosmos was ending, whether they understood what would follow their universe's death, whether they tried to leave any message for whatever came after, we cannot know. The physics of the bounce or the conformal transition does not preserve messages. It preserves quantum states, but quantum states are physical things. They carry correlations, they carry patterns, and those patterns, propagated through the bounce, became the initial state of our universe. The specific statistical properties of the CMB fluctuations that we measure today are, in these frameworks, the transformed remnant of the quantum state of the previous universe at the moment of its final compression. We are, in a very literal physical sense, reading what the previous universe left behind every time we analyze the temperature map of the oldest light in our sky. The lives and deaths of stars in the previous universe were not events disconnected from our history. In the bouncing universe picture, the specific distribution of matter in the previous universe determined through the quantum bounce the specific initial conditions of ours. The galaxies that formed in the previous universe, the stars that ignited within them, the supernovae that scattered heavy elements into the surrounding gas, the black holes that accumulated at galactic centers, all contributed to the quantum state of the previous universe at the moment of maximum compression. That quantum state, transformed by the bounce, became the initial quantum state from which our universe grew. We are, in a literal physical sense, the downstream consequence of stellar life cycles we can never observe. Across all of the pre-Big Bang frameworks explored in this story, a common thread emerges that is philosophically unprecedented. Information does not vanish at the Big Bang. Gravitational imprints, quantum correlations, statistical patterns, structural signatures of the previous era's black holes, and large-scale structures, all of these can, in principle, be transmitted through the bounce, the brain collision, or the conformal transition and encoded in the initial conditions of the new universe. This is a profound departure from the standard picture, in which the Big Bang was a complete erasure of any prior history. In the bouncing and cyclic models, the initial conditions of our universe are not arbitrary. They are not drawn from some uniform distribution of equally likely possibilities. They are determined, at least in part, by the specific physical state of whatever existed before the Big Bang. The universe we live in is the causal successor to something that came before it, shaped by events we can never directly observe, but whose consequences we might be measuring every time we study the structure of cosmic microwave background. The significance of this for the deepest question in cosmology, the question of why the universe has the specific properties it has, cannot be overstated. The apparent fine-tuning of our physical constants, the precise values of gravity and electromagnetism, and the cosmological constant that allow atoms and stars and life to exist, might not be a mystery requiring explanation by an external designer or by anthropic selection from an infinite multiverse. It might be an inherited property, the specific set of constants and conditions that the dynamics of the bounce selected from the quantum state of the previous universe. In that case, the explanation for why we exist is that we are what the previous universe produced, shaped by a physical process that traces back through the bounces as far as the chain of bounces extends. The problem with this explanation is that it generates an infinite regress. If our initial conditions were shaped by the previous universe, where did the previous universe's initial conditions come from? From the universe before that. And where did those conditions come from? The regress never ends. Every question about origins in the cyclic picture has an answer that defers to the previous cycle, and every previous cycle had a cycle before it. The question of why the universe exists with these specific properties ultimately dissolves into the question of why the cycling itself exists, and to that question no physical theory currently offers an answer. The specific predictions about what information the CMB carries from a pre-Big Bang era depend on which pre-Big Bang theory is correct. Loop quantum cosmology predicts specific modifications to the primordial power spectrum at large scales. The ekpyrotic model predicts a specific absence of primordial gravitational waves and specific non-Gaussian features. Penrose's conformal cyclic cosmology predicts the Hawking points. Each of these predictions is in principle distinguishable from the others and from standard inflation. The challenge is that all the predicted signals are subtle. The next generation of CMB experiments, combined with gravitational wave detectors and large-scale galaxy surveys, will together constrain which pre-Big Bang scenario best matches the totality of what we can observe. Every theoretical framework for the pre-Big Bang universe arrives, eventually, at a question that physics cannot currently answer. If the universe is cyclic, what drives the cycle? If it is eternal, why does it exist rather than nothing? If it emerged from quantum tunneling, what is the quantum state that describes the tunneling, and where did that state come from? Every answer generates a deeper question, and each deeper question is harder than the one before it. The infinite regression carries practical scientific weight as well as philosophical weight. It has a specific, uncomfortable structure. In the bouncing universe, each previous universe had its own previous universe. In eternal inflation, the inflating background had been existing before any particular Big Bang for an unknown and possibly infinite time. In the string landscape, the landscape itself has no origin. Each framework that successfully describes a physical process before our Big Bang does so by embedding that process in a still earlier context that is itself unexplained. Physics is not uncomfortable with deep explanatory taking chains. The history of science is a history of successive deepenings, each answer revealing a more fundamental question below it. What is matter made of? Atoms. What are atoms made of? Nuclei and electrons. What are nuclei made of? Protons and neutrons. What are protons and neutrons made of? Quarks. What are quarks? Nobody yet knows at the level below quarks. Each layer of the explanation was a triumph, but each also revealed another layer below it. The pre-Big Bang question has the same structure, but the layers do not obviously terminate. In every cyclic or eternal model, the chain of explanations seems to extend backward without limit, and the unease this generates is both scientific and something deeper. It touches something in the human instinct that everything must have started somewhere, that existence must have a reason, that the chain of causes cannot be infinite. Physics, in its current best developed forms, offers no comfort on this point. The infinite regression of predecessors in cyclic cosmology forces a confrontation with the nature of explanation itself. In ordinary science, an explanation traces the chain of causes backward until it reaches fundamental facts taken as given. In physics, those facts are the laws of nature and the initial conditions of the universe. But in cyclic cosmology, there are no absolute initial conditions. Every set of initial conditions is the outcome of the previous cycle. Every physical state is explained by the prior physical state. The chain never reaches a foundation. It goes backward forever, always deferring to the prior cycle. And what counts as an explanation in this framework differs fundamentally from what counts as an explanation when the story has a beginning. Consider what the fine-tuning of our universe's physical constants actually means in the context of a cosmos with an infinite or cyclical past. The strength of gravity, compared to the other fundamental forces, is extraordinarily weak. If it were significantly stronger, stars would burn too quickly and collapse into black holes before generating the complex chemistry that life requires. If it were significantly weaker, matter would never have clumped enough to form stars at all. The ratio must be within a narrow range for any complex structure to exist. Similar constraints apply to the electromagnetic force, to the masses of fundamental particles, and, most severely, to the value of the cosmological constant, the energy of empty space, which must be extraordinarily small compared to what quantum field theory naturally suggests it should be. In the eternal inflation and string landscape framework, these constraints are addressed by the anthropic principle. There are enough different bubble universes with different constants that some of them, by chance, have constants in the range required for observers to form, and we inevitably find ourselves in one of those. The fine-tuning is not mysterious. It is a selection effect. In the cyclic models, a different kind of explanation is possible. If the physical constants evolve or are reset with each cycle, and if the dynamics of the bounce or the brain collision produce a distribution of constants that is weighted toward values permitting complex structure, then the apparent fine-tuning might be an attractor of the cycling dynamics rather than a random fluke. This kind of explanation is more specific and potentially more testable because it makes predictions about what range of constants we should expect to observe given the dynamics of the cycle. Neither explanation is fully developed or confirmed. The anthropic approach requires an untestable multiverse. The cycling explanation requires a physical mechanism for resetting constants that has not been identified. But both approaches agree on one thing. The specific constants of our universe are not eternal facts about reality. They are contingent facts about our particular instance of cosmic history, shaped by whatever processes, cyclic or selective, produced the universe we inhabit. The fact that we exist to ask these questions is, in itself, a constraint on cosmological theories. Any viable theory must produce a universe where intelligent observers can arise. This is not trivial. Many of the possible string vacua do not permit atoms. Many do not permit nuclear fusion. Many do not permit complex molecules. Only a tiny fraction of all possible physical laws are compatible with beings who can ask questions about those laws. The universe we inhabit is in that fraction. Whether this is because selection from infinitely many universes inevitably lands us in a habitable one, or because cyclic dynamics naturally evolve toward life-permitting constants, or because of a principle not yet discovered, remains one of the deepest open questions in science. The final and deepest question raised by everything in this story is not a scientific question at all. It is a question that science can sharpen but cannot fully answer. What does it mean for a conscious being to exist in a universe that has no ultimate beginning? Humans have always structured their understanding of existence around the concept of origin. Every culture, every civilization, every religious and philosophical tradition has answered the question of where everything came from with some version of a first cause, a creator, an original moment, a ground of being from which all else followed. The scientific story of the Big Bang seemed to support this intuition by providing a precise, observable, calculable beginning to the universe. 13.8 billion years ago, everything began. Before that, the question was meaningless. The pre-Big Bang theories examined throughout this story replace that beginning with something that cannot be absorbed into the concept of origin. If the universe is eternally cyclic, with no first cycle, then there is no origin. The universe has always been here. It did not begin. It does not require a cause, because the concept of cause requires a before and an after, and in an eternally cycling cosmos, the before extends forever. If the universe emerged from quantum nothing through the Hartle-Hawking no-boundary framework, there was a beginning but not a cause, because the beginning had no preceding state from which it was produced. These answers are not satisfying in the way that a creation story is satisfying. They do not resolve the mystery. They dissolve it, leaving behind a deeper mystery. Why does anything exist at all? Why does a universe, or an eternal cycle of universes, or an eternally inflating multiverse, or a quantum fluctuation from nothing, exist rather than pure non-existence? Physics can describe how the universe evolved once it existed. It can describe transitions between cosmic states. It can show that the Big Bang was not the beginning. What it cannot do, at least not yet, is explain the existence of existence. The discovery that the Big Bang was not the beginning will take its place alongside the other great revolutions in cosmological understanding. The discovery that Earth is not the center of the solar system. The discovery that the galaxy is not unique in the cosmos. The discovery that the universe had a beginning 13.8 billion years ago. Each revolution removed a form of cosmic centrality from human experience, replacing a smaller and more comfortable universe with a larger and more indifferent one. The discovery that even the Big Bang is not a true beginning continues this process to its logical endpoint. We inhabit a cosmos that did not begin for our benefit, that has been running in some form forever, and that will continue forever after we are gone. This is the full weight of what the physics is currently telling us. The next decade of science will bring instruments that will probe closer to the Planck wall than anything before them. They will not cross it, but they will read the light on this side of that wall with a sensitivity that currently exceeds imagination. And in that ancient light, in the patterns of temperature and polarization and statistical correlation, they will look for the signatures that each pre-Big Bang theory predicts, and the others do not. The answer that emerges from that search will not be comforting in the way that a clear creation story is comforting. It will be a physical answer, specific and quantitative, about the nature of the transition that produced our universe. And whatever it says about what came before, it will confirm what the mathematics has been suggesting for 3 decades. The Big Bang was a door, not a beginning, and something real was on the other side of it.